Okay, welcome to class 25, which will be the last lecture of the semester. And I, again, just wanted to finish up a few things. And today we're going to talk about Turing machines, so you've been exposed to those. And we'll finish up with an example of a Turing machine. Now, you'll notice a theme throughout the semester, and that was kind of a quest for more and more power to represent wider and wider families of languages. So we started off with like regular expressions, and then we moved to DFAs and NFAs, and found that all three of those were limited to regular languages. And then we kind of moved on to context-free grammars from there, and found that those were limited to context-free languages. And then we also introduced push-down automata, which are also limited to context-free languages. And there's some things we didn't get to in this class. Context-sensitive languages, meaning context-sensitive grammars rather than context-free grammars, and linear bounded automata. We didn't talk about either of those this semester, but those kind of increase the scope a little bit further. And we did talk a little bit about context-sensitive grammars, where the left-hand side, rather than being just a single variable, could be a variable in terminals on the left-hand side. But the idea here is that each of these kind of increased the scope of what we could represent as far as languages were concerned. So each method above is more powerful, but was still limited in what could be represented. So what we desire is a new kind of machine that has even more power than those. And what we're after is something that's kind of universally powerful. And so we desire a kind of machine that has a couple of properties. One is powerful enough to describe anything that could be computed, just like a real computer system. So anything that you could come up with a computation for, an algorithm for, and produce some sort of result, we want to have a machine that's powerful enough to do that. And notice that DFAs and NFAs and context-free grammars and push-down automata were not powerful enough to do that. So we want something more powerful, kind of universally powerful for anything that can be computed. And then we also want something that's simple enough that we can use it to reason and formally prove things about computation. So we want something that is not complicated like a real computer system, that's a simple model, works kind of like a DFA or NFA, but has more power to represent anything that's computable. So we started with DFAs, NFAs, regular expressions. They had limitations. We extended the capabilities of those, and we eventually got to the point where we used context-free grammars, but those weren't machines, so we added push-down automata, which were more capable than DFAs, could do anything that a context-free grammar could do, or represent any language that a context-free grammar could represent, but they were still limited. And one of the reasons that those push-down automata were still limited is they had this single stack of memory, and that stack had these limited abilities. We could only pop things off the top or push things on the top. And so what we're going to do with a Turing machine, or today, is we're going to make something more powerful. And we're going to kind of eliminate this kind of single stack with these limited push and pop capabilities. We're going to get something that's more capable than that. So what we're going to do is we're going to look at Turing machines today. And what a Turing machine is, it's like a push-down automaton, but we replace the stack with a readable, writable tape. And unlike a stack, that tape has the ability to kind of store data more like a memory of a computer. In other words, it can write stuff to it. We could read what's on the tape, and then we could index our position on the tape, either left or right. So rather than just simple push and pop, we have the ability to index left, index right, and then read what's on the tape and write something back to the tape. That's a Turing machine. It's like a push-down automaton, but with a readable, writable tape instead of just a stack. And that's named after Alan Turing, a famous mathematician, computer scientist, cryptanalyst, philosopher, a whole bunch of other things as well. Turing was incredibly influential in the early days of computing. You may have heard his name before. Involved in the kind of Bletchley Park in during World War II with cracking the Enigma code and a bunch of other things for the war effort in England. He was British. So if you're interested, learn a little bit about Alan Turing, but these machines were named after him. This is a concept he came up with. So let's look at the concept in more detail. So a Turing machine basically looks like this. We already said it has this kind of read-write head that's positioned on this tape. And the tape is kind of infinite in both directions. And then we have this machine controller that works kind of like a DFA, but that DFA controls whether this reads or what the head does. Does it go left? Does it go right? What does it put on the tape when it sees a certain symbol on the tape? So a couple things about that. I have some bullet points below. The tape is infinite length in both directions. It starts with the input on the tape with the head at the leftmost, that should say leftmost symbol. I don't know why it says right there. Leftmost symbol. So in other words, at the beginning of the input. All the other cells are blank at the start. So these have empty contents. There's nothing on these except for the input. So these ones here with nothing in them. There's a special input symbol on there that means blank tape. M is a finite state controller that determines the operation of which direction the head goes, and what gets written to the tape when it reads a certain thing from the tape. M starts in a defined start state, just like a DFA or NFA have a defined start state. And at each step of operation, M has to read the value from the current square, the current cell of the tape, and then make a decision. And what it makes a decision is what it writes to the tape, whether to move the head left or right, and then what the new state of M becomes. So it's just like a DFA that this changes from one state to another state. But when it changes state, it also will either move to the left or right, and it'll write something to that cell before it makes M move. Okay, a couple notes on the operation of this thing. Since M can move left or right, there's no concept of consuming input. So it's not like with a DFA where it uses up a symbol. It basically looks at the tape, reads what's there. The DFA or the finite state controller makes a decision on what the new state will be and whether, when it does that transition, whether it moves the head to the left or right, and what it writes to the tape before it moves to the next position. So M is going to continue. It's going to continue changing state, writing new symbols to the tape as it goes, moving to the left or right as it goes, and it's going to run until it reaches what's called a halting state. And what a halting state is basically just a state where the machine stops. And so that halting state where the machine stops is important because notice that once we reach that halting state, the machine just shuts down. It does not continue ever out of a halting state. When it hits a halting state, the machine is done. So note that it's possible to define a Turing machine that never reaches a halting state. It could run forever. And notice the input string has to be finite, meaning that the thing that this starts with has to be a finite length string, finite sequence of symbols. That's what the definition of a string is. And so there are always going to be a finite number of non-blank tape cells. We could add more to it and write to the tape, but it's always going to be a finite number of non-blank tape cells. All right, so let's look at the formal definition of this. So that's the basic idea. We have this read-write head. The state controller says with this symbol under the read-write head, we make the decision to write a new symbol to the tape, move either left or right, and then change state to a new state based on the DFA or the finite state machine that's inside of the finite state controller. And note that that has to be finite, that this is a finite thing. You can't have an infinite-sized controller, and you can't have an infinite-sized input, and you're never going to have an infinite-sized number of symbols, non-blank symbols on the tape. So this is still a finite machine. All right, here's the formal definition. The formal definition looks a whole lot like the formal definition for a push-down automaton. In fact, it's a sextuple, just like the push-down automaton has the same things. The only thing that you'll see that's different is a couple things. We'll see that in a second. One is the transition function is mapped differently. The other one is this, rather than being a stack alphabet, it's a tape alphabet. We'll talk about that in a second. And in some treatments of this, instead of this being called F for the set of final states, it's just 8. Sometimes they'll call it H for the halting states. But whether you call them final or halting, they're really just a subset of Q, just like F was before. So if you look at stuff online, you might see this set called H. But in other words, this looks exactly like a push-down automaton, but we have the transition function is a function instead of a relation, and we have this tape alphabet down here rather than a stack alphabet. All right, so let's focus on that transition function and what makes it different. Well, first off, let's just go through these. So Q is a finite non-empty set of states, just like it was for DFAs and NFAs and push-down automata. Sigma is a finite set of input symbols. That's our input alphabet. The only rule about that is, well, it has to be finite. And those input symbols cannot contain the empty tape symbol. So the empty tape symbol has to be completely distinct and not also in the input alphabet. So the empty tape symbol is like a special symbol that can't be part of the input alphabet. Delta is this transition function. It maps elements of Q minus F, in other words, the non-halting states, the non-final states, and tape symbol pairs. It maps those to the output symbol that goes onto the tape, which is either one of the new... Actually, I need to fix something. Hold on, I'm going to pause for a second and fix that. Okay, the thing that was messed up is there's a typo with an extra cut and paste thing left in there. So what this maps is elements of the non-final states and the tape alphabet to something new in the tape alphabet along with a new state and either action to go left or right. So notice that makes sense. So what we're mapping is non-halting states with read symbols we read from the tape. We're mapping that pair to a new resulting state and the right symbol that goes on the tape and the head action. And note that that transition function has to be finite. So the initial state or start state is an element of Q, has to be one of the start states, and then our set of final or halting states has to be a subset of our set of states. Now, the finite set of tape symbols can contain, or has to contain at least our input alphabet, because the input starts out on the tape, and the empty tape symbol. But it could contain other symbols that aren't part of the input alphabet. There could be other symbols that are part of this as well. Things that get written to the tape that are not part of the original. We're going to see that in our example we do here in just a little bit. Okay, so continuing on here, let's look at one of those transition function elements. So if the transition function contains an entry Q0A, and as the kind of domain element, and then the range element is Q1BL, then what that means is that the Turing machine, if it's in Q0 and there's an A under the read head, then the machine will change to state Q1. It'll write a B, and then it'll move to the left. So it changes to this state, writes this to the tape, and then it moves. It doesn't move and then write. It writes and then moves. So this A that was on the tape is going to get replaced by that B. We're going to change the state machine to Q1, and then we're going to move the head one position to the left on the tape. All right, so a few more notes about the operation of this thing. And let me go back. A couple quick notes about the, let me move this over just a little bit there. Okay, a couple notes about the operation of the machine is that the empty tape symbol, we're going to represent, it can be represented in a number of different ways depending on what book or reference you're looking at. It might be represented by like the C language \0 to represent the null character, or it might be the empty set symbol, or it might be $, or sometimes it's a £sign or something else. Sometimes it's a period. But anyway, whatever the empty tape symbol is, it's in all of the cells except the input cells. In other words, that infinite tape that goes in both directions, all of those cells are empty except for where the input is. And since the input string, the input alphabet, cannot contain the empty tape symbol, you're guaranteed that the input is kind of isolated and not to be confused with empty tape. So the input's not allowed to contain the empty tape symbol. The machine is however, allowed to write the empty tape symbol. And all state symbol pairs have to be defined in delta for non-halting states. So, and that's sometimes relaxed. If you don't have a state symbol pair, then you can just consider the machine as stopping. But generally, for the formal definition, you're supposed to have a total function for every non-halting state. But in practice, just like with DFAs, if you leave those out, you consider it as rejecting that or exiting, halting when you get something that isn't defined. All right, so delta is a function, so that means that operation is deterministic. In other words, there's never any choice. When it sees a certain symbol and it's in a certain state, there's only one action defined for that. Since it's a function, you can't have more than one domain element. So it's always going to be completely deterministic. So the machine can be considered to produce output, and in other words, when the machine halts, whatever was on the tape could be considered its output. So you can feed it input, it can process things, it can produce an output. All right, so I think what will make the most sense for understanding this is let's look at an example. And let's look at one that we've actually seen before. Let's look at this A to the N, B to the N. Now this was not regular, so we couldn't do this with a DFA. We could represent it with a context-free grammar, and we could represent it with a push-down automaton. But in this case, we're going to do one, we're going to make a Turing machine that does it instead. So here's the concept of how we're going to write this machine. And there are other ways you could write this as well. But what we're going to do is the machine is going to start on the leftmost symbol. We're going to say, when I see an A, since we need to see a number of A's followed by a number of B's, what I'm going to do is I'm going to mark off that A with an X. So we're kind of going to, whenever I see an A, we're going to put an X over it. And then we're going to scan ahead until we find a B. When I find a B, I'm going to mark that off with a Y. So I find the leftmost A, put an X, find the leftmost B, put a Y, and then I'm going to scan backwards again until I get to the X, and then I'm going to find the next A. So the next A, I'm going to mark off, the next B, and then I scan to the right until I get to a B, I mark it off, and then I scan to the left until I see an X, and if I don't see an A after that, I scan this way, and then I get to the end. And when the machine stops, if there are no A's or B's left in the string, then that string all of them got marked off. So remember, we're marking off an A and then a B. We're doing them in pairs. So if we mark all of them off, all of them are marked off, then that string is an L. So that's our output. In this case, said, hey, we had 2 of those and 2 of those. They both got marked off. This string is accepted. All right, so let's make the Turing machine for this. Let's start off with the easy stuff. So the easy stuff is the alphabet is just A and B. The tape alphabet is A, B, but then we were marking things off with X's and Y's, so we need to add those. And then we need to have the empty tape symbol. In this case, I'm just using \0. All of you have had like a C programming class and are used to that concept of a null character. So we're just going to use that throughout this example. Now you might see other resources or books that use some other symbol. We're just going to use that \0 character. All right, so this is the alphabet. That's the tape alphabet. Now, the rest of the parts of this, the way that I designed this, it's got 5 states, Q0 through Q4. Starts with Q0. Only one halting state is Q4. And basically what these states end up being in here are the ones that are saying scanning to the left, looking for an A. Once we mark it off, we scan and look for a B. Once we mark that off, we scan back to the right, looking for the X, and once we find that, we go back to the state that scans for the A, marks it off, scans for the B, marks it off. So you're going to see these states having those different functions when we do this. This is what the transition function looks like. There's a D there. It changed the font on me, so let me fix that real quick. And I apologize for fixing these as we go, but I want to make sure the slides are clean and I don't forget to fix any of those things. Now, so this is what my transition function looks like down here. And this will make more sense when we look at this as a graph. So let's take a look at that as if it were a graph rather than, in this case, just all of these transition things. But one thing to note is, before we go to look at the graph, look at what this is saying. This is saying if I'm in state Q0 and I have an A, then when I take that edge to Q1, I'm going to replace this A with that X and move to the right. This is saying when I'm in Q1 and I see an A, then I go to, and this is wrong here. I need to fix that. Again, this was late last night that I was preparing this. So this Q1 needs to stay there on an A. Let me fix that too. I don't know what Q sub A is. Q1A. There we go. All right, so this is saying when I'm Q1 and I have an A, I stay in Q1 and I leave the tape alone. In other words, I take the A off the tape and I rewrite an A. That's effectively leaving it untouched. And I move to right. So in other words, when I just see A's, I just move to the right. When I see Q1 and a Y, I replace it with a Y. In other words, I leave it alone and I move to the right. So whether I see an A or a Y, I just scan to the right. But if I'm in Q1 and I see a B, then I go to Q2 and write a Y over the top of the B, and then I move to the left. So let's look at the graph. I think it'll make a lot more sense when we look at the graph. So here's what the graph looks like. So in other words, if I'm in Q0 and I see an A, I write an X and I move to the right. Now that's writing that first A. Now I need to scan until I see a B. So whether I see another A or a Y, I just continue along to the right, leaving the tape alone. There's a Y, leave a Y, read an A, write an A, move to the right. So this is just scanning to the right, going over the top of all of the A's and all of the Y's. Now, as soon as I see a B, I say that's the first B I encountered that would match this first A that I wrote the X over. So I write a Y over the B and now start scanning to the left. So this is now scanning to the left. So over here, now whether I see Y's or A's, I keep going to the left until I get back to an X. The X representing the first one I marked off. So as soon as I see that, then I move back to the right. I leave the X intact. I move to the right. So I'm over the top of the first A again, or the Y. So when I get back to Q0 here, I'm going to be over an A or a Y. If I'm over an A, then I need to mark that one off and mark off the corresponding B. So this is the A. This is its corresponding B. So we mean every A we mark off, we're going to mark off a B. And then we jump back here, and eventually we'll get to the point where all of them are marked off. We will then take this path here to get that Y. Once we get the Y, then we go over the top of all of the Y's until we get to the null character at the end, the empty tape, and then we halt. All right, let's trace through this with an example string. So let's try it. So here's an example string, 4 A's followed by 4 B's. And the head starts out over that leftmost symbol, and the rest of these are empty tape. Okay, so what's the first action that we would take here? So let's look, we start in Q0, and notice I'm representing what state I'm in here in parentheses. So I'm starting Q0, I see an A that I read. So I take this path labeled A, the transition labeled A, and what do? I write an X and move 1 to the right. So there I wrote the X, and I moved 1 to the right, which now puts me over this next A. But now I'm in state Q1, because now I'm over here in my finite state machine. And so now I'm in Q1 and I see an A. So what do? I write an A and move 1 to the right. So I wrote an A, left it there, moved 1 to the right. Same thing is going to happen again. Write an A, move to the right. Now I'm still in Q1. So let's reset this back to the top. There's where I am right now. So I still have an A. I'm still in Q1. So that loops back to Q1 again and moves 1 to the right. But now I see a B. So now notice in my state machine over here, I'm going to take this path, this B with a Y. So now I see a B. I replace it with a Y. But now I move to the left. So now I'm scanning back to the left again. And now I'm in Q2. So now that I'm in Q2, whether I see A's or Y's, I'm going to keep scanning to the left. Left, we're still over A, so here's where we are now. Still in Q2. We see an A under the read head. Leave the A alone, move to the left. leave the same situation here, leave the A alone, move to the left. Now we have found an X, so we're in Q2 on an X, so now we're going to take this transition over the top here, back to Q0, and notice we're going to put an X, leave the X there, but move to the right. So now we're going to be back to the right. So the situation we're in is now we're over that A, and we're back in Q0. So when I see an A, I mark it off with an X and move to the right. There's the X that I just put down, move to the right. And now I see an A, I leave the A and move right. See an A, leave the A, move right. See a Y, leave the Y, move right. And now we're over a B. So we're down here in Q1 with a B. We're going to write a Y and move to the left. We wrote the Y over the top of that B. We move to the left. Now we are in Q2. We have Y. We leave it and move left. Still in Q2. A. Let's transition over here. Leave it and move left. Still in A. Leave it and move left. Now we have an X. Leave the X. Read the X. Write the X. Move to the right. So now we're back in Q0. We have another A. Replace it with an X. Move to the right. Have another A. Now we're in Q1 though. So leave the A and move to the right. Leave the Y. Move to the right. We're in that state. Q1 with a Y. Leave the Y. Move to the right. Oops, I jumped too ahead that time. Now we are over the B. Leave the B. Or mark the B out with a Y. Move to the left. And now we're over Y. Move. And now we're in Q2 and we have an A. So we move to the left again. We got to that X in Q2. We relieve the X and move to the right. But now we're back in Q0. We see the A. That takes this transition right here, the one from Q0 to Q1. Mark that one out. Jump to Q1. Now Q1 is going to see 3 Y's in a row, so this transition right here. The Q1 on Y stays in Q1, but writes a Y and moves to the right. So we're going to do that across all of the Y's. And now we're on the last B, which is going to be this one here. Mark that out, move to the left. And now we're in Q2. We're just going to go across all of these Y's here. Y, Y, and now Q2 with a Y. We do it one more time. Now we're on an X, so we go back to the back to Q0. And now we see a Y instead of an A, so we're no longer going to match an A and a B. So now we see that Y. We're going to jump down to Q3 and leave the Y alone. And that's just going to consume all the Y's now down here in Q3, looping back to itself. So 3 steps doing that. And then finally, we move, consume, or go across that Y, go 1 to the right there. Now we're on the null. And in the null, we leave the null there, move to the right. And at that point, we halt. We've hit this halt state. So state Q4 is defined as a halting state, so the machine stops. And since we look at the tape and there are no A's left and no B's left, the string gets accepted. Now, what's interesting about this, couple final thoughts about Turing machines, is that they aren't much more complicated than a push-down automaton. In other words, instead of having a stack that you push and pop, they have a tape that you read and then write. And notice that a push-down automaton had a separate input stream and then it had a stack. This doesn't have that. This is in some ways simpler because it only has the tape. And the tape has the input, and the tape also acts as the memory to store things and do things. Now, what's interesting is something that simple can handle any computation that can be performed by a computer system, anything. So you play a game, you have a computer system that can play chess at like a 3300 level, well beyond what any human can do. You could actually implement that on a Turing machine. So it's kind of amazing to think about that. But the idea here is that they're in practice, they're kind of inefficient and impractical because they're so simple. But that simplicity is also what makes them useful. That because they're so simple, we can use them to prove things about computation and prove things about fundamental limitations of computing machines by focusing on something that's so simple. That we have this finite state machine, we've got this tape. You can read from it, you can write to it, you can move to the left or right. But even with that simple machine like that, what Turing did when he created this is he kind of boiled down computing into like the simplest sort of machine that he could imagine. And it doesn't have all the complexities of a modern computer, so that allows it to be used as an abstraction tool to study parts of computation. And there's some really fascinating things that he came up with it, and also some things that are outside of the realm of what can be computed. And you can use Turing machines to prove those as well. So one of the examples of that is what's called the halting problem. And the halting problem is, let's say you want to write a computer program that you feed other programs into, and it tells whether or not they will eventually stop. Or let's say you want to feed in a Turing machine design into a Turing machine and have it tell you whether or not that Turing machine will halt or whether it will run forever. And it turns out that that's impossible. That's something outside of what you could ever write a computer program to do. And that seems a little bit odd when you think about it. Why can't you write a computer program that will analyze a computer program and decide for any computer program you fed in whether or not it would stop or not? And it turns out that it's impossible. And you can prove that with a simple proof by contradiction using Turing machines as kind of the logic behind that. And I would encourage you to Google that. Google the halting problem. Look at a YouTube video or read the Wikipedia entry for it. It's really fascinating. And it turns out there are other problems that are outside of the realm of computation as well. There are things that you just cannot compute using. There are things that computers just can't do. They're outside of the realm of what's computable. Not in a practical sense, just in any sense. And the halting problem is one of those. Okay, so one final thing related to Turing machines is this concept of what's called Turing completeness. And what Turing completeness is a machine that exhibits Turing completeness has the ability to simulate all aspects of a Turing machine and therefore compute anything that is computable. So a programming language that's considered Turing complete is capable of computing anything or accomplishing any task that a machine could ever do. That sentence is a little messed up. I'll fix that here before I post the slides. But in other words, if a programming language is Turing complete, it can compute anything that a computer could ever compute. And most programming languages are Turing complete, like Python, C, C++, Java. Those are all Turing complete. Some languages, however, might not be. Things like PostScript and actually PostScript might be, or HTML. There's some things like that that are considered programming languages, but they're not Turing complete. But one of the things about that is there are also some like toy languages or esoteric languages that are Turing complete. Like there's a language called Whitespace. There's one called BF that is like this really weird bunch of garbage that you write. Looks like weird symbols that are actually a programming language, but they're still Turing complete. You can compute anything with them. Notice that the whole concept of Turing completeness is interesting to think about. A simple machine like a Turing machine, which is really simple to understand, can do anything that a computer can do. And a computer can perform any task that is computable as long as that you can show that it's Turing complete, which computer systems are. And there's some power behind that, understanding that it helps Turing. What he did when he created these things, he helped define the limits of computation in a formal way to say, like, okay, this is something that can be computed, this is something that cannot, and you can actually prove certain things. So in other words, there's certain problems that no matter how hard you tried and no matter how much you worked at it, you could not write a computer program that would ever solve those problems. You could not, and that would include any kind of technique you would try to apply, genetic programming, like machine learning, dynamic programming. You could not. There are certain problems that you could just never solve with a computer. And that's a kind of a fascinating concept to think about. All right, so the last thing here is let's go back to the Chomsky hierarchy for just a second here with one more thing. And this one more thing here with this Chomsky hierarchy, notice that we started out with regular languages. We then expanded to context-free grammars and pushed down automata. And then we didn't really spend much time looking at this context-sensitive languages, linear bounded automata, or context-sensitive grammars. We also didn't spend any time looking at what's decidable versus semi-decidable. But notice Turing machines are in this outside thing. They can do anything that any of these other ones can. So if you have a regular language, you can make a Turing machine that accepts that. If you have a context-free language, you can make a Turing machine. If you have something that's context-sensitive, make a Turing machine for it. But there are things that live outside of here that are non-decidable or non-computable things, like the making a program that tells if another program will stop or not and give an answer, cannot be done. Okay, so that's it for this semester. I hope you guys enjoyed the class. I hope you learned something. And one of the things that was important to me after I had learned automata, that it changed how I approached a lot of problems. If you're ever writing a program where you need to write your own programming language, which you're going to have to do next semester in the compiler class, you're going to be using context-free grammars. You're going to be using finite state machines. You're going to be using a lot of these things that we talked about in here to do that, because there's no better way to approach that kind of problem. If you try to hack together a compiler, it's going to be a rough road for you. But if you start out with a grammar, context-free grammar for that language, and you use like a state machine-based parser, then you're going to have a pretty easy time of it. Now, a couple other things like hardware design, protocol design, minimization of hardware designs, all of that stuff is stuff that can benefit from what we've done here. Game design with a non-player character, where it has different states, where it's scared, it's angry, it's happy, it has a different behavior when you attack it versus when you help it. Those kinds of things. Again, finite state machines can help with that. And if you have something that's dealing with natural language processing where it needs to understand a human language sentence, things like context-free grammars, or there's a special subset of this stuff called link grammars, which are a form of context-sensitive grammar, can help with parsing English language or producing English sentences. Again, in your game, you want to have some range of options and some decision tree. Finite state machines are perfect for that kind of thing. You want to have some game you make that has emergent behavior, like ants building an ant hill and collecting food and or foraging for food, chickens that run around in the yard of your adventure game that you're writing, your fantasy game that you're writing, and they peck at things, but when you get near them, they run away and they're afraid. Again, this stuff that we were looking at here can really help you design pretty much anything, whether it's hardware, software, protocol, AI/behavior, and so forth. So this is really powerful stuff that we talked about. So I hope you enjoyed it. I hope you learned something. And that's all for today. And next class there is no class, no more things, no one more things ever, which makes me a little bit sad. And I hope everybody enjoyed our time together. And I would encourage you to keep in touch. And if you have problems with anything, even another class, or just want to talk about some stuff, kind of a huge nerd and enjoy that kind of thing. So keep in touch. Everybody stay safe. And hopefully I'll see you around, and hopefully I'll be able to take a look at some of your senior projects when you present those, and hang out with you guys a little bit next semester. So that's it. Stay safe. Have a good break, and hopefully I'll see you guys around. Do keep in touch. That's it.